Okay, well, I wasn't expecting this to be today, but guys, this is our last set of notes for Chem 30 then. After this, we're done learning new content. I don't know that you guys clued into that yet. So, okay, so a quick reminder, just in case you watch the video again. So today we'll do our lesson notes. Then tomorrow we'll do a quiz. Friday is Tiger Day, so I don't really know. Do you know much about how that's going?
I think there's going to be like the first two classes.
Oh, so we would still have like an hour or so. Okay. So I mean, we can use the first hour or so on Friday just for catch-up time. And then next week, basically, the plan would be to do one more quiz and one more unit test. I guess maybe we'll try to do the lab on Monday then. It's really not a hard lab. It basically consists of we're going to well, let me just show you real quick one more time what the plan was. You know how you make an ice table here? And usually I give you a number in the top corner, like say 0.10 moles per liter. And then this you don't count, this is 0, goes up by x, x, down by x. And you just leave this as 0.10, you know, like that typical table we just did. We're going to try to do that in real life. It's just we need to do a couple of things to test. Okay. In order to get this initial concentration, there are two main ways of calculating a concentration. One is that you make it yourself from scratch, and that's definitely possible. The other main way of finding a concentration is to do a titration. And so that's what we would do is we're going to do a titration, try to calculate how much moles per liter actually goes in this top corner here. Does that make sense? The other thing we're going to need to do is, since it's an acid, this will be H3O plus right here. We would like to know the H3O plus value. And there's a very simple way of doing that. We use a pH meter. Because if we can calculate the pH of this value right here, we can actually turn it into an H3O plus. Once we have those things, it's usually x squared over 0.10 is equal to your Ka value. The Ka value is in your data booklet, and so we should be able to compare the Ka value in your data booklet to the one that we are going to calculate. And I mean, it's really straightforward. You basically you measure the pH of it using a pH meter. That gives you this value down here. You titrate to try to get this number right here, and that's actually all there is to the lab. It's actually a very simple lab. It's mostly titrations. One of the reasons why I like doing this lab, though, is it dovetails really nicely with this last topic, which is something I like to think of this as like a leftovers lesson, where I've got a whole bunch of little random tidbits here, where they're kind of related, ultimately because they all involve acid-base equilibrium. They're also kind of related based on involving in titrations, but it's kind of herky-jerky. Like I just got like a bunch of random stuff on this, and then on this, and then on this. So I kind of put this all together right at the very end and just kind of finish off with all the leftover little bits. Does that make sense? So, okay, so let's get started here. The first thing I want to do is just remind you about titrations then, because you actually are expected in two different units to know how to do titrations. You should be able to do acid-base titrations, where you titrate an acid and a base next to each other, but you should also be able to do redox titrations. You guys remember how we did the redox titration where we had the purple permanganate stuff? We had to try to calculate concentrations using those as well. So you should be very prepared for titration type questions on the diploma. So here's some terminology. The end point and the equivalence point. And if I were to give you a graph like this, hopefully you've like seen graphs like this from grade 11, but if you haven't, there's a good chance you'll get one of these on your diploma. And I'll give you some on tests too. Basically what this is a graph of, it's the pH compared to how much titrant you add. The volume on the bottom here is how much titrant you add. So if we were to draw a bit of a picture here of what you would do in a lab, ideally we would have already done this lab, but you guys have done titrations before. Up here, this would be an acid, and the sample down at the bottom here would be a base. And as we add more and more acid to the base, it neutralizes itself. Does that make sense? So if we were to put a pH meter up top here, by virtue of this guy being a base, you'd have a very, very high amount of pH, right? And then all of a sudden you're going to add one drop of acid, and it's going to like stay pink. Does that make sense? And the reason why is that all of a sudden, as soon as you start adding some more acid, well, now there's no more base down in there in the bottom. All that's left is acid now, and so then the pH will just plummet. It'll just fall right off a cliff, and it'll end up having a very low pH. Right? And this point right here, this is the point where you usually want to stop your titration, and you stop it based on the color change. So the words we would use is an end point. The end point would be, I usually refer to it as where the pH would be. it's when the pH would be, ideally, it would be 7, right? Because if you have an acid and a base neutralizing each other, the neutral is 7, right? 7 is pure water, right? So that would be your endpoint. It's usually where it's pink, because usually we're using phenolphthalein. You don't have to use phenolphthalein. There are other indicators, and I'll talk about those today as well. But that's our endpoint. The equivalence point is this volume right here. And so the equivalence point would be, it looks like about 24 milliliters, right? It's when you stop, it's how much volume have you actually added by the time you're done. You guys remember those terms? Okay. Today we're just going to focus on them a little bit more in the context of how it applies to equilibrium. So, first thing I want to do is I want to talk about something called a buffering region. I have that listed in a few different places here. Buffer is a word that you found in different places in different subjects. Do you guys talk about buffers in social studies? Have you guys ever talked about buffer states? Or is that not something you've covered? Okay, grade 12. Do you guys do buffer states? It's been a while. Yeah, in like use World War II as an example. When Hitler was trying to take over different countries, I don't know that this necessarily was coined around that time, and my social studies is not maybe the greatest, but like a buffer state would be where you have a country between you and somebody else. So like if, you know, Nazi Germany is right here and you're over here, the buffer state is the country in between you where you realize we're safe, right? Because in order for Hitler to attack us, he'd have to go through this country first. Does that make sense? So that's where buffer gets used in other places. It means something completely different here. So what I just told you is probably not really relevant to anything. This right here is known as a buffering region. Okay. In chemistry, a buffering region is a place where the pH is not changing all that much. Okay. Sometimes it's very important to have pHs made very constant. For example, if anybody has a hot tub, you need to maintain the pH balance of a hot tub because you don't want it to have too high or too low of a pH, because if it becomes too acidic or basic, I don't know which way is which anymore, but if it becomes too acidic perhaps, then it's hazardous to a person. But if it becomes too basic, then it allows bacteria to grow, and that's also bad because there's fungus growing in your hot tub, right? So you want to try to maintain a fairly constant pH value. Your blood actually has a pH balance buffer inside of it, where you don't want your blood to become too acidic or too basic, because again, that causes major problems in your body. So long story short, a buffer is a place that resists pH change. This essentially is what you need to know. I like the word resist. You don't want to have much pH change. It needs to be very, very level in terms of your pH amount. Hopefully in this graph you guys can visibly agree. Right here, is the pH changing a whole lot? No. I mean, is it changing? Yeah, sure, it's changing, but is the pH drastically changing? No. And then right down here, is the pH changing? No. Right here, though, in the middle? Yeah, that pH changed like crazy. This would be a very bad buffer right about here. That makes sense? Because all of a sudden the pH just tanked, right? And if this was your hot tub, this could be bad for you, right? Because if this was a safe level on your hot tub, and the pH all of a sudden tanked like this, well, now maybe it's too acidic. Now you're going to burn the people who are in your hot tub with acid burns. That'd be bad.
Yeah.
Lawsuits. So sometimes we refer to it as something like the leveling effect. All right? I mean, a buffer basically is where it's very level, right? Where does the buffer fail? Well, it finally fails near that equivalence point, right? The equivalence point being that volume where, like, the titration was able to add a whole bunch of volume to it, right? Right here, how much volume was it able to add before it finally failed? It was able to add about 24 milliliters. And at that point, and then finally the buffer ran out, it wasn't able to handle it anymore. And the pH finally had to tank. So, do you guys, have I ever used the word inflection point before? For the two of you who are in calculus, you guys do inflection points, right? You guys talked about inflection points? Oh, okay. Never mind then. Let me just point out what an inflection point is. This right here is called an inflection point. Mathematically, on a graph, an inflection point is where it goes from having like a negative sort of slope. You guys see how the slope right here is always kind of going downhill right now? But then all of a sudden it starts kind of changing and kind of leveling off a little bit flatter. I like the example of Kinsey on the slide. When she's going down the slide right here, this is like her falling off the cliff kind of concept, right? and this is where she speeds up. But then this portion of the slide right here, this is the portion of the slide that makes it kind of safe for her because it's gonna like slow her back down again. Does that make sense? Right? You could have a slide that looks like this, where you like fall right off the cliff and then it slowly but surely kind of levels out. Like think West Edmonton Mall water slides. You know that one where it just basically you just fall right down, right?
I don't like that.
Right? If it wasn't for the fact that there was an inflection point, if it just kept doing that for forever, that'd not be it'd be a great water slide, but you probably wouldn't live, right? So an inflection point is where the slope kind of changes, if that makes sense. So it used to be slope that was like I said, it used to be slope that was kind of like this, and then all of a sudden now it's slowing down a little bit. So mathematically, this is known as an inflection point in between like two halves of a graph. All of you I've taught math to, I believe. Maybe think of it this way. Think of it like here there's a quadratic. You guys see how I've drawn a quadratic like this? And then here I've drawn another quadratic. Only rather than drawing them both as quadratics here, let's draw this one fairly flat because it needs to be a buffer where it does not change all that much. And then rather than turning back around like this, let's have this one kind of flatten out there. So imagine that you have two consecutive quadratics. The place where those quadratic meets, that would be known as an inflection point. Okay, so it's a mathematical term, but it essentially refers to what we've been talking about. This is your endpoint. It's also your equivalence point. Okay. How do you know when you've reached this inflection point? How do you know when your graph then has, how do you know when to stop doing your titration? Well, we usually use indicators. The most common indicator that we use is phenolphthalein. But truth be told, phenolphthalein is actually kind of cheating a little bit. Because what's the pH range for phenolphthalein? It goes from about 8 to 10. So phenolphthalein goes from 8 to 10, but where is probably the inflection point supposed to be? Well, it's probably supposed to be somewhere around 7 in a lot of cases, right? So we actually cheat sometimes when we use phenolphthalein because it actually is a little bit too far up. Phenolphthalein's range would actually be right about here, and so when you start to notice it, it's actually going to be right about there, which means that, I'm not drawing this real great here, but it means that your volume is actually a little bit lower than it probably should have been. Does that make sense? But we accept that as a trade-off in a high school lab for a couple of reasons. The main one being that it's really easy to see when the color change occurs on phenolphthalein, because phenolphthalein goes from clear to pink, and it's so distinctive when the color change occurs. Probably a better indicator to use would be bromothiamyl blue, which is probably the indicator you guys are going to be using when we do our lab final. When I guys have you do the back titration of a Tums tablet, we'll probably end up using bromothiamyl blue because of the fact that when we crush up the Tums tablet, you guys know like what a Tums tablet looks like, right? We're not going to use the colored ones. We're going to use just a basic white one. But when you crush it up, it makes it very, very cloudy inside the solution, and it makes it very hard to see the pink. So because of that, using phenolphthalein becomes less effective, because why would you use phenolphthalein if you can't see the pink color, if it's obscured by like the white of a Tums tablet? So we'll probably end up using bromothiamyl blue, which means it would change from blue down to yellow. And what would you see in between as a color? You see green. So this is where it becomes a bit more subjective. As soon as the blue starts looking green, we have to stop. Does that make sense? If it goes all the way to yellow, that's fine, but we might have overshot it. And you want to look for, rather than the faintest bit of pink, you're looking for the faintest bit of green. So it makes it a challenge. So, okay. Yeah, you guys can read the rest of this. Okay, let's move on to the next concept. So that basically was my first little bit of leftover bit. You guys should know how to basically interpret an acid-base graph and know those terminologies to it, and know what a buffer is. So long story short, a buffer is a place where the pH doesn't change, because we don't want the pH to be drastically different. While I'm talking about indicators, I need to point out something. So I have like so many words on the slide. Let me just talk somewhere different. You guys know that acid-base indicator table? It's in your data book. You have it nearby. We really only use this in grade 11 so far, but it's actually meant to be used in grade 12 as well. And I have only seen this done a handful of times, but I need to point something out. Do you guys see the table? Off on the far side, in the far column there, see how there's Ka values? Acids and bases indicators are actually acid-base indicators. They actually have Ka values. And so it's very possible that they're going to give you a question on an indicator where you have to do some sort of calculation. And in order to solve the calculation, you might need the Ka value. Because what really happens is acid-base indicators are actually equilibrium systems. There's actually an equilibrium going on inside those indicators where you've got both acids and bases together. Let me see if I can try to describe how this works using this picture here. This would be a basic litmus kind of idea here, where what's actually occurring when you put litmus or bromothymol blue or whatever indicator you have, there's actually a whole system inside that drop. Where there's actually an acid and a base both collectively there. This side might be, say, red, and this side might be blue. Or it just depends on whatever colors it is. It could be yellow and it could be green. I don't know what the colors have to be. But what ends up happening is, let's say you put this in an acid. Well, if you put this in an acid, what ends up happening is it ups this concentration right here. Well, what would happen according to Le Chatelier's principle if you upped this concentration right here? It would shift it that way, causing it to make more of this chemical right here, and this chemical right here would be red, which is why acids and litmus are red. Does that make sense? But the way litmus works then is, if it's a base, if you add this to a base, what the base is going to do is it's going to drop this guy's concentration because it'll neutralize this amount of H3O+. Well, then it's going to cause it to shift this way. So if you put an indicator in a base, it'll actually turn blue, which is why litmus is red in an acid and blue in a base. We've never actually talked about this before, but acid-base indicators are actually Le Chatelier's principle applied to acid-base systems. Does that make sense? That's the reason why they change color, because either what ends up happening is it ups the acid concentration and shifts this way to one color, or it tanks the acid concentration and shifts back the other way towards the other color. So, long story short, I need you guys to be able to recognize that acid-base indicators are actually equilibrium systems. When I give you those dropper bottles, there's actually an equilibrium system inside that dropper bottle. Hence the whole reason why we better actually close it up, because you don't actually have it evaporate. Right? And then as you add it to an acid or a base, it shifts one way or the other based on color. So, other thing I need you guys to be able to do then is, if it comes up, and this is rare, but I've seen it before, if it comes up, recognize that because it's an acid-base system, there's a Ka value attached to it. So they might actually ask you the question where they want you to find the hydronium amount based on methyl red. Right? And so then you have to go to methyl red and say methyl red has a Ka value of 1.0 times 10 to the minus 5. You might have to make a nice table for it. So. Here's just a slide just reminding you of the fact that they have all these different color shifts. You know, some of them actually occur in more than one spot. I want to tend to take a second here to talk about thymol blue. If you guys can take a look in the data book at thymol blue is the third one down. And what's special about thymol blue is that it actually has two systems. It actually has H2TB. By virtue of being H2TB, what it can do is it can turn into H1TB, and then it can further turn into TB2 negative. And so it actually has two different ranges. And the whole reason is based on this H2 right here. Do you guys remember the term polyprotic or poly something? Let me give you some other examples here of just regular acids you'd recognize. HCl. HCl breaks up into H plus and Cl minus. It just does it once, right? But here's a polyprotic acid, H2SO4. It can turn into H plus and HSO4, and then the HSO4 can turn into an SO4. Do you guys recall this concept of like having more than one proton on it? Or like poly something? Right? So by virtue of it being able to react more than once, that's actually why thymol blue has two different color ranges. It goes red to yellow, then yellow to blue, because there's actually two protons. First, it could lose its first proton and just have one left. And then it can actually lose a second proton. And that's actually something else I talk about later in the slides here. So that's my next topic here. You should also know about polyprotic things that can do more than one proton. So let me show you a picture of one here. Here's an example of a titration of Na2CO3 and HCl. Let's talk about this one for a sec here. What is HCl? It's an acid, right? Hopefully you recognize that. Further than that, though, HCl is a strong acid. So like it always reacts 100% of the time. But what about Na2CO3? What's happening if you have an Na2CO3? Well, essentially what you have is you have what I listed down here. You have an Na plus and you have a CO3 minus. Well, it's actually the CO3 minus that really matters, because what's going to happen is that CO3 minus is going to react and it's going to pick up one proton and turn into HCO3. But is HCO3 done reacting? I'd say, well, no, because HCO3 can pick up another proton and become H2CO3. So this is why this is actually a polyprotic reaction. There's actually two equivalence points. There's an equivalence point right here where CO3 turns into HCO3. And on the second slide, there's a second equivalence point where the HCO3 turns into H2CO3, where you can actually have two reactions. And so this would be one of the first times now where we need to start talking about how, does the endpoint have to be at 7? And the answer is, well, no. If you're adding a strong acid and a strong base to each other, it seems very likely to be at 7 because it neutralizes to water, and water's pH is at 7. But hopefully this is a good example of a picture type graph where here the pH endpoints right here, one is at about 8, one's at about 4. Should you use phenolphthalein for this endpoint right here? Actually, it's not a bad idea. Phenolphthalein changes color right around 8 to 10, so that's not bad. But should you use phenolphthalein for this endpoint right here? No, it wouldn't work at all, right? Because the endpoint is supposed to happen at about a pH of 4, so you better pick a different color. So it is possible to actually have two different endpoints inside a graph, and that's because it would be a polyprotic graph. You guys can basically read through the rest of the slides there, but have I made my point fairly well? That from here to here, what's happening is your CO3 minus has turned into HCO3 minus, and then here it's turned into H2CO3. Each time it added a proton. Here it added a proton. Why are we done right here? Because it can't pick up another proton. Do you guys know of anything that has the ability to do it 3 times? There's usually only one chemical that we talk about that does it 3 times. PO4. If it's a PO4, a phosphate has the ability to actually react 3 times. Because PO4 is a 3 minus, right? So for every minus it has, it can pick up an extra proton. Okay. Okay, here's a word that I haven't used in a while. Remember the word quantitative? Quantitative means that it reacts like 100%. Okay. Like 99.9%. It really is not reacting at equilibrium. This is a pretty rare thing that comes up here, but you know how you have like your table right here? I mentioned there's a page break in the middle. If you react something with a strong base, and the only strong base, by the way, is hydroxide. If something reacts with OH minus, and usually the acid is above wherever HSO3 happens to be. So where's HSO3? HSO3 is right about here. If anything from here and above reacts with that strong base.
Mr. Forster, can you please call 100?
Usually it's not at equilibrium anymore, because the strong base is so strong that once it picks up its proton, it really doesn't give it back anymore. So if you have like from here reacting with here, or from here reacting with here, or here reacting with here, or if I hold this thing up right here, here's the H2SO3. If anybody above my index finger here tries to react with a strong base, it actually doesn't usually react at equilibrium anymore, because the strong base is so strong. Once it takes the proton, it doesn't give it back. You know how there's that whole 2 ants going both directions here? The 1 ant is just too strong. He doesn't let the other ant go the other way. So I don't know whether you maybe want to put a little marker there on your table, but I basically just say for HSO3, anything above that, if and only if it reacts with hydroxide, and then it's actually not equilibrium. I also have a similar note here for acids here and how it works with NO2. So if you happen to have the same table right here, if you have any of the strong acids up here and it tries to react with NO2 or anything below NO2, the strong acid is so strong that if it tries to react with something down here, really we don't bother writing an equilibrium arrow anymore, because it really is not an equilibrium. The strong acid is so strong that it always gives away its proton. It doesn't take it back ever. So you might end up seeing something like this. H3O plus adds to HCO3. You see how I just wrote the single-sided arrow? I don't bother writing the double-sided arrow because this H3O plus and that HCO3 right here, they're so far apart that it's not even worth it to write a double-sided arrow anymore. So you may just want to put two little markers there. Anything lower than NO2 and anything higher than HSO3. But that's only if it's with a strong acid or base. Only with the strong ones, okay? By virtue of them being strong, they're so strong that once they either give away their proton or they take the proton, they don't want to change. So if you give away your proton, you don't want it back again if you're a strong acid. And if you're a strong base, once you take that proton, you don't actually give it back away at the end of the day. So that's what some of these slides talk about. All right. Okay, another piece of leftovers here. While I'm talking about polyprotic things, you know how some of these things have the ability to give away more than one proton or take more than one proton? Well, it means it has more than one Ka value then. So you might notice that in this table here of indicators, you know how in the indicators table there's thymal blue? It actually has two Ka values. The same thing actually applies for certain acids. For example, citric acid. Citric acid actually is H3C6H5O7. See how there's three hydrogens right there? That's polyprotic. It has the ability to give away hydrogens 3 consecutive times. Well, because of that, there's actually 3 different Ka values. So I need you guys to be aware of the fact that you might actually have to search for the right Ka value, because you might be talking about the first proton it loses, or the second proton it loses, or the third proton it loses, because it actually will happen in 3 different stages. As a graph, this guy probably looks something like this. There's the first proton it loses. There's the second one. There's the third one. So each of these, this one, this location, and this location, they'd each have a Ka value then. For things that have more than one Ka value, what do you notice about the comparison between the two? This is 10 to the minus 5. That's 10 to the minus 12. It is always smaller. Always, every single time. Here it's 7, then it's 11. Here it's 3, then it's 8, then it's 13. Every time it loses a proton, it finds it harder and harder to do so. So each time that a subsequent reaction takes place in one of these polyprotic things, it occurs less frequently. Less frequently. So like here, it might lose its proton 12% of the time. Well, then here it might lose its proton 1% of the time. And then here it might lose its proton 0.001% of the time. So I need you to be aware of the fact that every time one of these reactions occurs, the subsequent reaction is less frequent. The Ka value always drops. Okay, lastly, because of the fact that there are different strengths of acids, there's actually different types of graphs that we have. I actually have been lying to you. Normally when I show you a graph, I usually show you it like this, and I tell you the pH is right here at 7. And like that is true many, many times, but it's not exactly, it's a partial truth. I actually need to show you some different graphs, some different pictures of graphs now for these last slides. This one here, maybe I'll come back to this picture. I'll just do these ones one at a time here. Let's say you had a strong acid and a strong base react. Would it be at equilibrium if a strong acid and a strong base reacted? And I'd say no. Because what does a strong acid want to do? It wants to get rid of its proton. What does a strong base want to do? It wants to take a proton. Once the guy gives away the proton, once the guy takes the proton, are they going to want to go change back to where they started? If you are strong, no, you don't. Because by definition, that's why we call them strong. They're called strong because they don't reverse their reactions. So what ends up happening is these guys have very nice, clean reactions where you have a nice starting point right here. It drops really high like that and then stops. And the equivalence point for anything that is strong is usually at 7. The reason why is because all of the protons get transferred, and therefore there's no acid left, there's no base left. It's perfectly neutral when you have strong and weak things react. And this is what you've normally been shown for a graph. But like I said, I've been telling you kind of a partial truth. So now I need to rectify that. Let's say that you have a strong acid and a weak base. What does a strong acid want to do? Strong acids want to get rid of their protons. What do weak bases want to do? Well, bases would like to take a proton. But if you're a weak base, you're reluctant about taking a proton. Does that make sense? And since the weak base is kind of reluctant, sometimes the weak base sends the proton back. I don't know, use a restaurant analogy. The acid is the kitchen. The kitchen is giving you food. And the weak base, you are the patrons of the restaurant who is accepting the food. And once in a while, you send the food back. Does that make sense? A strong acid, strong base relationship is you eat your food, you love it, sounds great, right? But as a weak base, sometimes you might not actually keep your proton. You might send it back to the strong acid. And what that ends up doing is it actually drops the equivalence point because it doesn't actually get rid of all of the acid. Not all of the acid is neutralized. And so it might actually drop the equivalence point to be a little bit below 7. Normally, the equivalence point would be at 7. But if you have a strong acid overpowering a weak base, the equivalence point might actually drop down to, like, say, 6 or 5. So sometimes I've kind of been lying a little bit about where that equivalence point is. It doesn't actually have to be at 7 because it really depends on strength. If one is stronger than the other, it'll overpower it. Now, if they're both strong, that's perfect. But if one is strong and one is weak, it drops the equivalence point here. And then here's the reverse of that. What if you have a weak acid and a strong base? Well, a weak acid kind of wants to get rid of its proton. The strong base takes it all the time, right? And so what ends up happening here, this will actually cause the equivalence point to maybe be a little bit higher. Rather than having the equivalence point being at 7, it might actually up the equivalence point to being at 9. So you know how I've mentioned that we sometimes cheat when we use phenolphthalein? Actually, sometimes we're not cheating. Because if I ever give you a strong base and a weak acid, usually the equivalence point would be somewhere between 8 and 10, which is just dead perfect for phenolphthalein. So now if I ever make you to titrate a strong acid and a strong base, phenolphthalein is probably not appropriate. But if I make you titrate a weak acid and a strong base, then phenolphthalein is dead perfect because we expect the pH level to be slightly higher based on the fact that the strong base is going to predominate in this relationship. So I feel like that kitchen analogy. The kitchen kind of wants to send out food but is really unsure of it. And as a strong base, this would be like you running into the kitchen and like stealing the food off of the stove. Like here you are just like saying, no, taking this. No, I'm taking this, right? And the acid doesn't really want to give away its proton. So it ends up being slightly more basic than it normally would be. Is this going to be at equilibrium? Well, remember, we just talked about this a second ago. If the strong base or the strong acid is reacting with somebody too far down on the table, then no, it really doesn't actually occur at equilibrium. So most of the time, these things are not equilibrium systems. Which leads us to the last one here. What if you have weak acids and weak bases reacting with each other? Well, then you end up getting a graph that looks something like this, where it's more like like there's not really much of a sharp change. It doesn't have like a nice little twist to it. It just really kind of just slowly but surely goes uphill. And the phrase we'd say here, it doesn't really have an equivalence point. It does not have one because they're often not quantitative. These things are usually still at equilibrium. So if you ever try to titrate a strong acid and a strong base, pH is 7. Strong acid, weak base, lean towards the acid. Weak acid, strong base, lean towards the base. If you ever try to titrate a weak acid and a weak base, they really don't have the ability to like fully have this proton always change place because it's like the hot potato. This guy will give away the proton, this guy will take it back. He'll give it and take it back. And so you constantly are in this state of flux where protons are constantly changing hands and you really don't get a nice specific curve. So you really can't do a titration of a strong acid and a weak base. And if they give you a picture of a graph, you'll notice it because the graph doesn't have that nice little shape to it there. The other thing you'll notice is that the starting point right here is actually fairly high. Right, like look at the initial pH value. It's at about 3. If it was a strong acid, the pH value might start down here at 1. Let me just compare here and I'll show you again. See how here there's a weak acid? The weak acid has a pH starting value that's a little bit high. Like it's not really all that low. It's a pH of 3. It's still an acid, but it's not nearly that high. Here, look what happens when I have a strong acid though. The strong acid value starts down here at 1 because that's what a strong acid would do, right? A strong acid might probably have a lower pH. Why does a strong acid have a lower pH? What do strong acids do? They get rid of their protons, always. If you always get rid of your proton, it means you're always making hydronium. And if you always make a lot of hydronium, well, the formula is negative log your hydronium. That's how you calculate your pH. So strong acids usually have the lowest of all the pHs. So you can also tell these graphs based on how low the graph starts. If it starts really low, it's probably a strong acid. But if it starts a little bit higher up, it might be a weaker acid. So what I need for you guys to be able to do then is be able to look at a graph and kind of interpret what's happening. So let me just show you a couple of graphs here. Okay, what's happening in each of these graphs? If this is like the pH along this acid here, what sort of things are reacting in this titration? And a strong base. I'd say this is strong acid and strong base. Now it's got a nice clean pH point, and I'm going to guess it's probably going to be right at 7. What's happening in this one here? Which one's the strong one? Which one's the weak one? Is it the base that's strong or the acid that's strong? Which one? The base is the strong one, yeah. Because I can see the pH point looks like it's a little high compared to normal. So for the pH to be higher, it must be a strong base with a weak acid. Different question here. Who's the titrant? Is the acid the titrant or is the base the titrant? If I were to draw a picture of like a lab setup, who is where? Is the strong acid in the flask? Or sorry, is the weak acid in the flask and the strong base in the burette, or vice versa? The weak acid would be in the flask. And the reason why is that as I measure the amount of pH, the pH is acidic to start, and as I drop in a strong base little by little, it's making the pH slowly but surely rise up. So the strong base would be here, the weak acid would be there. What's special about this one? There's actually two things about this one that I want to point out. Why are there two little bumps? Because there's a polyprotic something, yeah. Something is polyprotic. Now it could be the acid, it could be the base. I'm not actually sure which one it is, but there's definitely something polyprotic occurring. Okay. And then secondly, if I ask you where the two things are located, where is the acid and where is the base on this one? Yeah, the base is the sample this time. This guy right here is the base, and this guy right here is the acid. Because what's happening is we're starting with a basic pH, and as we add more acid, drop by drop by drop, it's reducing. So I need you guys to be able to look at a graph like this and interpret what's occurring. Is it a strong acid or weak base? A weak acid is strong base. Strong and strong. Is one of them polyprotic? Which one is the sample? Which one is the titrant? So. Okay, that should essentially be it, I think. Do I have much left? Oh no, I do have more left. So here's a summary slide of that. Of course. Yeah. Usually they just check in with me at the beginning of the class, and if they do a quick check-in, then they can go off to the library or somewhere else. And then they're considered here, and if they didn't do a check-in, then they mark us away. Yeah. Okay. Yeah. Yeah. Because he left me his notes that 2 kids did check in. So checking in on that. Yeah, that was probably just missed that. That's not. Okay. Sorry, guys. Okay, this is I think this is my last little section here. I want to re-talk about buffers one more time then. So buffers, one more time on a graph here. Buffers are places on a graph where the pH doesn't change all that much. Hopefully you'd agree then that right here the pH isn't changing all that much. Right here the pH isn't changing all that much. But right here, yeah, the pH is changing a lot. So then the question might be, well, how do you make a buffer? How do you make a system where the pH doesn't change all that much? And so here's the definition of how that works. What you need is a weak acid and its conjugate base. In order to make a buffer, you need a weak acid and its conjugate base. So let's talk a little about why we need that. Let's say you use a strong acid. What does a strong acid do? Well, a strong acid gets rid of its proton. all the time, which means it's going to react quantitatively 100% of the time. If it's always getting rid of its proton, that's a huge problem, because what's going to happen is it's going to cause the graph to plummet like this. At some point here, it's always going to be getting rid of its proton, and you won't have a buffer. So you want someone who's a weak acid so that it can get rid of its proton, but it can take it back again if it needs to. You also want to have its conjugate base. And the reason why you want that is because you need something on the table. You guys know how you have like your data booklet table? Here's like the fold line. You want to have a weak acid, and you want to have its conjugate base so that it's right next to each other. So you can have this guy turn into this one, turn back to this one, turn to this one. If you were to use somebody else's base, what's going to happen is these are actually going to react with each other. These two things will undergo a reaction. And I'd rather actually have it basically just go just between these two things right here and constantly change back and forth. So let me give you an example of a buffer, hopefully here. What's happened here is we took NaOH and we added it to acetic acid. So what's occurring in this particular location right here, which is known as a buffer region, is the CH3 COO minus that you'd get out of this guy right here is going back and forth with the CH3 COOH. What you actually have right here is a weak acid, and as it gets neutralized, it's turning into its conjugate base, but it's turning back and forth over and over and over again. And what ends up happening is you have a system here where you have both acid and base. You have this guy as the weak acid, but as you burn up the weak acid, it creates another weak base over here. Well, the acid prevents it from getting too basic, but the base prevents it from getting too acidic. And so it's actually the best of both worlds. You have an acid to protect against any base that gets added, but you also have a base that gets used to protect against any acid that gets added. Here's where the base fails. Here's where the thing fails, though. At this point right here, the buffers are going to fail. And the reason why it's going to fail is that we finally run out of our weak acid. All the weak acid is finally gone, and so there's no more weak acid left to protect, and so it's going to cause the pH to all of a sudden rise up. Does that make sense? So this is officially what the equation was. I didn't write down everything there, but essentially what's happening is your acid is turning into a base. This weak acid is turning into a weak base. But what's going to end up happening now is you have both. You have acid and you have base. Okay? The acid will prevent it from getting too basic. The base will prevent it from becoming too acidic. And the pH should be fairly level until either this guy right here is completely gone, or until this guy right here is completely gone. So, let me give you just an example of a question off a diploma. Which is a buffer? I'll just give you some examples. Which of these things could be a buffer? Can you guys see it? Which one of these has a weak acid and also contains its conjugate base? B is the right answer, yeah. I kind of tried to make this a little bit easier. This guy right here, hopefully you'd agree. That guy's a weak acid. Can you guys pick out why it's a weak acid? I mean, it's on your table. It's got an extra proton right here. It's actually polyprotic. You can actually lose both of these protons. But the reason why it's at a buffer is that this piece right here is its conjugate base. So what you end up having is, here's a weak acid, it will protect against any bases. Here is a base, it will protect against any acids. And these two things can just keep turning into each other. If you were to have a weak acid and somebody else's conjugate base, they would react with each other. Right? They'd actually undergo some sort of chemical reaction and they'd change what you'd end up having. So here's a picture that basically just describes what would happen to a buffer. Let's say that you had a buffer and you added some base. Well, the acid part of the buffer would prevent the pH from rising until eventually you run out of acid. At this point right here, the acid would run out and then the pH would rise. Or let's say you were adding acid. Well, then the base part of the buffer would be good until eventually it runs out. So like here, you'd have some CH3COOH, and then eventually it runs out right here. Or here you'd have some CH3COO negative, and eventually right here it would run out. So at some point the buffer will fail. If you add enough stuff to it, the buffer can't actually last anymore. Oh, my voice is almost done. Okay, so today's lesson was kind of a hodgepodge of just random stuff. I need you guys to know about buffers. I need you to be aware of titrations again and how they work. Indicators. Indicators are actually a system, an equilibrium acid-base system, where what ends up happening is you have color changes depending on Le Chatelier's principle. So the last stuff that we've covered here is mostly just random little tidbits. So none of that was intended to be on the quiz, obviously. So granted, there's not much time left today, but did you guys get anything accomplished assignment-wise yesterday? Did you get fairly far at all, or no? Okay. If you guys happen to have a chance, maybe see if you can ask some questions later today. I know I'm running out of time today, but let's try to write a quiz tomorrow, and then Friday, I guess we'll have. I guess we'll have a little bit of time in the morning on Friday. Okay. If you want to ask questions right now, feel free. I guess I do have about 10 minutes left.